Inside every internal combustion engine, a precise and violent chemical reaction is happening hundreds of times a second. Igniting a compressed mixture of fuel and air generates a massive amount of heat energy right in the core of the engine block. This chart maps where that energy goes. About 1/3 is converted into useful mechanical work. Another portion exits immediately through exhaust gas. But a critical, large percentage remains as residual heat, trapped inside the metal cylinder and piston head. If that residual heat has nowhere to go, it accumulates stroke after stroke. The engine reaches its first major failure state, overheating. Under severe thermal stress, metal parts expand beyond their tolerances. Pistons can score the cylinder walls or seize entirely. Furthermore, extreme temperatures cause the engine's lubricating oil to thin out and lose viscosity, destroying the protective film between moving parts and accelerating mechanical wear. However, we cannot solve this by simply driving the temperature as low as possible. Keeping an engine too cold triggers the second failure state, overcooling. When an engine runs too cold, fuel doesn't vaporize efficiently, causing fuel consumption to spike. The lubricating oil remains thick and sluggish, failing to coat parts properly, which drags down overall engine efficiency and increases internal friction. The cooling system functions as a high-precision thermal regulator, maintaining a specific operating temperature by constantly balancing heat rejection against heat retention. The simplest method to regulate this temperature is air cooling, which relies entirely on ambient air to draw heat away from the engine block. The engine requires a specific modification, cooling fins. These ridges increase the cylinder's surface area. Because heat transfer relies on contact, maximizing surface area exposes hot metal to passing air currents, continuously pulling thermal energy away from the combustion chamber. For examination purposes, the advantages of air cooling are straightforward. It requires no water pump, it needs no radiator, and almost zero maintenance. The construction is entirely solid state, making the engine significantly lighter and immune to freezing in cold climates. Because of weight savings, air cooling is standard on scooters and motorcycles, where the engine block is positioned perfectly to catch high-velocity oncoming airflow. However, passive fins provide poor, non-uniform temperature control. Once you increase engine size or enclose it under a hood where natural airflow stops, air cooling fails rapidly under massive thermal loads. Industrial power and enclosed automobiles require a different approach. To prevent thermal meltdown, they rely on a forceful, closed-loop fluid solution. This is liquid cooling. For heavy-duty automobiles and industrial power plants, like diesel locomotives, the massive thermal output makes passive air cooling physically impossible. The working fluid in these systems is commonly referred to as coolant. It is a precise mixture of water and antifreeze that serves multiple thermodynamic purposes. It raises the boiling point, lowers the freezing point, and actively prevents internal corrosion. The liquid cooling loop begins at the source of combustion. The engine block contains hollow passages surrounding the cylinders, known as the water jacket. Coolant rests inside this jacket, directly absorbing the violent heat from the metal walls into its fluid mass. But if this heated liquid simply sits inside the jacket, it will boil, and the engine will melt. The system requires mechanical force to move the fluid, which is provided by the water pump. Driven by the engine, this centrifugal pump forcefully circulates the heated coolant, pushing it out of the water jacket and into the closed loop. Without the constant mechanical rotation of the water pump, circulation stops, and the entire heat exchange process collapses instantly. The water jacket captures the thermal danger, and the water pump provides the required physical force to drag that danger away from the engine core. Once the pump pushes the boiling fluid out of the engine, it sends it to the ultimate heat sink of the system, the radiator. The radiator maximizes thermal rejection. Hot fluid enters the upper tank, flowing down through thin vertical tubes connected to metallic fins. Heat transfers from the liquid to the fins, dissipating into ambient air. At the bottom tank, the fluid's temperature drops significantly. Because this process requires constant airflow, the system includes a cooling fan. When a vehicle is idling or moving too slowly to generate natural wind, the fan activates to forcefully pull air through the radiator fins, ensuring continuous heat rejection. The radiator is sealed tightly by the radiator cap. This is a crucial pressure control valve that regulates internal pressure. By keeping the fluid pressurized, it raises the boiling point of the coolant. allowing the engine to safely operate at higher temperatures. Together, the radiator and fan act as the system's exhaust port for thermal energy. They dump the heat of combustion into the atmosphere, so the chilled coolant can return to the engine block to repeat the cycle. This creates a thermodynamic conflict. If the water pump is always pushing fluid and the radiator is always chilling it, how does a freezing cold engine warm up properly on a winter morning? To solve the overcooling paradox, the system relies on the thermostat. This is a strict temperature-controlled valve placed between the engine block and the radiator. This flowchart illustrates the decision logic. When you initiate a cold start, the thermostat remains tightly closed. It completely blocks access to the radiator, forcing the coolant to loop endlessly inside the engine's water jacket. By bypassing the radiator entirely, the engine retains all of its combustion heat. This allows the metal and lubricating oil to rapidly accumulate thermal energy and reach their optimal operating temperature without delay. Once the coolant inside the block hits that critical operating temperature, the internal sensing element expands. The valve springs open, instantly unleashing the boiling fluid into the radiator to be chilled. This automated cycling based on real-time thermal conditions keeps the engine in equilibrium, protecting the metallurgy from heat damage while preserving overall fuel efficiency. When we combine these parts, we get a fully integrated liquid cooling loop, continuously transporting thermal energy away from the combustion chamber. To trace the exact flow of thermal energy for diagnostics and exams, remember this path. Heat moves from the engine into the coolant, passes through the water jacket, travels to the radiator, and is rejected into the atmosphere. This cyclic flow chart shows the mechanical loop. Coolant is drawn by the water pump, pushed through the engine jacket, and returned. The thermostat serves as the temperature control valve, dictating flow, and the radiator acts as the primary site of heat rejection. Applying this to heavy industrial engines requires complex architecture, heavy-duty pumps, and massive radiators to handle extreme thermal loads. This is a stark contrast to lightweight applications, which operate reliably with nothing more than passive fins and steady ambient airflow. A cooling system is an active, continuous balancing act. It constantly adjusts fluid dynamics and airflow to tame the intense energy of internal combustion. Mastering this logical chain, from heat generation to fluid transport to atmospheric rejection, is the necessary foundation for diagnosing engine failures and understanding the physical laws of thermodynamics.